Okay, everyone, so let's see the graph of the effect of labor growth, or in general, we call it population growth. So you have already seen a graph in one of the previous videos about the break-even point and the representation of the steady state. So this one is graph number 2. And if you already understood graph number 1, then this one would be easy, because now we're not changing saving ratio, which is the S, as we used to do in the graph number 1. In this graph, we are going to see the effect of N, where N here is I'm just going to change the color here. So let me use red. So here we're going to see the effect of the increase in population growth from N1 to N2, or the effect of the growth in labor. So as you can see, N only comes in this line, which is the blue line. Okay, I want you to understand something. This like maroon color line, which is called investment. The blue line is called break-even investment. In graph number 1, in one of the previous videos, we called this blue line as depreciation. In this graph, we just rename it and we call it its break-even investment line. So this is break-even investment line number 1. This is the new, or the break-even investment line number 2, that is changing because of the change in N, or the labor force growth rate. So let's take it here. If we look at the first intersection point, which is the intersection between investment curve and break-even investment line. So we have an intersection at K1 star, which is the amount of capital labor ratio at the steady state. So what's going to happen if there is an increase in N, or there is an increase in labor growth rate? If labor growth rate increases, then we're going to have a rotation in the break-even investment line from this one to this one. So we have an upward shift because of the increase in N from N1 to N2. A very important thing to notice is the difference, or the gap, that is that we have between this new point and this point. So this gap basically implies that D plus N2K, D plus N2K is greater, right? Is greater than SFK. In other words, the negative effect on the steady state exceeds the positive effect. How this would affect the steady state? If I have a negative force that is higher than the positive force, then I would expect the steady state to decrease. So we will have a decrease in the steady state from K1 star to K2 star. And we will reach a new steady state in which we have an intersection between the investment curve and the new break-even investment, which is D plus N2 times K. Okay? So if you understand this one already, then the last part of the Solow model is basically, so we said the first one was what's the impact of saving ratio, the second one what's the impact of population or labor force growth, and the last one what is the impact of technological change. The technological change that we will talk about is something related to augmenting the quality of workers that we have. So you can think of it as manufacturing robots, or as computers that the labor force are now having, things that we're going to increase the quality of workers. I want you to think about N as the quantity of workers and T as the quality of workers. And if this is called the increase in the labor force, the percent of the labor force, or the growth in the labor force, then we can call G as being basically the increase in the effectiveness of workers in terms of their quality. So if you're going to accept this assumption, then it's easy to update our equation and say then the change in K is going to have a positive force, that the one that we used to talk about, which is investment, but our negative impact will not only have a depreciation rate, will not only have the growth in the labor force, but will also have the growth in labor augmenting or the effectiveness of workers. And everything is multiplied times the capital to labor ratio. We said that these two together are called the dilution rate. Okay, so this is the dilution rate from the increase in the, or from the growth rate of workers. What's the amount of capital I need to increase to maintain the steady state? And this is exactly the same reasoning. What is the growth in capital that I need in order to maintain the steady state because of the increase in the effectiveness of workers? If I can have this positive force equal to the negative force combined, then I can say that the change in K would be equal to 0, will not move either left or right. Right? In the previous graph, for example, we had the negative force exceeded the positive force, so we had to move towards the left. So if you accept this, like this assumption of having a positive force investment, we subtract out of it the negative force of depreciation, growth in the workers, or the growth rate of workers, and then the growth in the effectiveness of workers, then we can easily have a new graph, where the new graph, and we're not going to talk about it in details because it's just a repetition. So if we look at this last graph would only have a change in the line that we call a break-even investment. So the line that is called a break-even investment will have now G. And that's the only change. So we have an investment curve, but our blue line, which is called the break-even investment, and remember, this one used to be, in the first graph, used to be called depreciation line. But then we just rename it and call it break-even investment, because anytime this line, the maroon color line, is going to hit this blue line, then it's going to be called a break-even investment. So for simplicity, it's called break-even investment. So the point at which we have K star here is simply called the break-even investment, at which we have the positive force is equal to the combination of the different negative forces, or 3 negative forces. And of course, you can just repeat the same analysis that we had in the previous slide. What's going to happen is G increases. So if G increases, just look at this graph and just repeat the same reasoning. If G increases, then I'm going to have like a line here in which I have D plus N constant, but I have, let's say, G2. And everything is multiplied times K. And then you just talk about the same exact reasoning. Okay, so you can also read your textbook for more details on these graphs. All right, if you have any question, please post on the discussion board. Thank you.